All right, let's do a few more examples of induction. This one's a little bit different because we're dealing with an inequality here. But the basics are going to be the same. And I think with all of these, it's a really good idea for you to try them yourself, or at least get as far as you can through an induction problem, at least setting it up. And then watch the video to see if the things that you are doing are matching with the things that I am doing. So maybe right now I think a good idea would be to pause the video and try this one yourself. Okay, now that you're back, well, let's see what this is saying. So it says that for any n that is part of this set, which is the integers greater than or equal to 0. So we have a least element here, which is 0. So that is going to be the smallest case. That'll be our base case. And it says that 2 to the n is greater than or equal to n. So let's prove this by induction. Oh, I want my black pen here. Okay. So let's do our base case. Remember, that's the gasoline that starts our machine working. We'll build our machine. And the second part, so this is when n is our least element, when n equals 0. Well, let's test it. Is 2 to the 0, is that greater than or equal to 0? And of course the answer is yes. 2 to the 0 is 1. That's greater than or equal to 0. So our base case is correct. The argument is true for the base case. Let's do our inductive case. So let's assume that for some k that is in our index set, which again are numbers 0 or bigger, I should say integers bigger or 0, that this holds, that 2 to the k is greater than or equal to k. So when n equals k, we're going to assume it's true, and we want to show that it's true when n equals k plus 1. So to show, we want that 2 to the k plus 1 is greater than or equal to k plus 1. So what we want to do is we want to think of a way where we can use our inductive assumption, or inductive hypothesis, which is that 2 to the k is greater than or equal to k. And kind of the key here is thinking, well, I can make a 2 to the k appear by just factoring in a 2 from this. This is the same thing as 2 to the 1 times 2 to the k. So if I have that, then I can use my inductive case. So that's the key here. Okay, now that we have our plan, let's consider 2 to the k plus 1. We want to show that that's greater than or equal to k plus 1. So that equals 2 times 2 to the k, which, well, we don't even want equals. We're going to replace this. Maybe I'll do this actually in line so that we make sure the inequalities are correct. If we replace the 2 to the k with k, using our inductive hypothesis, we get something smaller. So this is 2 times k. So that's what we're doing here, is we're using our inductive hypothesis. So let's tell people by the inductive hypothesis. Okay. And now we need to show that this indeed is true for k plus 1. And so you could write down, let me write this down on a different line. So this is 2 to the k. So what we want to do is we'd like to say that this is indeed greater than or equal to k plus 1. But this is only true when k here is 1 or bigger, when it's not 0. So only true when k is greater than or equal to 1. Okay, so what do we do here? So let's think about what we should do here. Well, we know this is true for n equals 0. It is true. But our argument, our inductive argument, is only going to work for k greater than or equal to 1. If instead of having z greater than or equal to 0, we had z greater than or equal to 1, so 0 was no longer in our set, we could treat 1 as the base case, and we'd be good to go. But because n equals 0, we kind of have this little hiccup. So one way to get around this is don't treat 0 as your base case. So change the argument entirely. Treat 0 as a special case, and then do this induction for z greater than or equal to 1 as your induction. And if you do 0, that special case, put them together, and you'll be good to go. So let's write down kind of the note here, because we'll have to do this again, but that's okay. Note, since this argument only holds for k greater than or equal to 1, we need to treat 0 as a special case. So I guess we should just rewrite this. It's all right the first time you do a mathematical problem. If you do it and you run into a hiccup that it doesn't work and you notice another way to actually solve the problem, then you just have to start from the beginning, but you know what you're going to do. So that's not a big deal. Let's scroll here and we'll just write it again. No problem. That's a nice thing about mathematics. Just because you write it down once doesn't mean that it's there forever. We can start again with something that's more correct if we need to. So, let's do it again. And then this is by induction. In fact, maybe I won't even write by induction first. Let's do two cases. Case 1 is that n equals 0. Then 2 to the 0 is greater than or equal to 0. So we're good to go. So our argument works in that case. In case 2, this is going to be when n is greater than or equal to 1. And we're going to do our induction now with 1 as our least element. We just separated 0 from that set to be a separate element. So now, let's write it up. So, our base case, let's say by induction actually. It's basically going to be the same argument, but we'll write it down all in one place for posterity. Our base case is n equals 1, then 2 to the 1 is greater than or equal to 1. Is that true? Well, 2 to the 1 is 2, sorry, and that is indeed is greater than or equal to 1. So we're good to go. Let's look at our inductive case. Let's assume, just like before, for some k in, but it's not going to be z greater than or equal to 0. It's going to be z greater than or equal to to 1 now, because remember, we separated 0 out as a special case. So assume for that 2 to the k is greater than or equal to k. And we want to show, of course, that 2 to the k plus 1 is greater than or equal to k plus 1. K plus 1 there, that looks a little bit better. And we're just going to write the same thing. So consider 2 to the k plus 1, which is 2 times 2 to the k, which is greater than or equal to 2 times k, and this is by our inductive hypothesis. And then 2 to the k, indeed, is greater than or equal. In fact, maybe I'll write it like this, so it's even more clear why this is true. This is k plus k, 2k, and that is greater than or equal to k plus 1 for all k that's greater than or equal to 1. Thus, well, what do we have? Let's put it all in one line just to make sure that people understand what we proved. Well, we proved that 2 to the k plus 1 is greater than or equal to k plus 1. And putting these cases together, case 1 was when n equals 0, and case 2 was when n was greater than or equal to 1. Putting those together, we have all of our index sets starting at 0. We just had to break off that little case when n equals 0 by itself. Let's try this one. This one's a little more complicated. So same idea. For an n in z greater than or equal to 0, so your whole numbers, that 3 divides 2 to the 2n minus 1. So again, give this a go yourself and see how well you can do. Okay, now that we're back, let's have a look at this. So let's do our proof. Again, we're always going to start with our base case. That's when n equals 0. Okay, so is 3 a factor of 2 to the 2 times 0 minus 1? Well, 2 to the 2 times 0 is 2 to the 0. And anything to the 0, except for 0, is 1. So this is 1 minus 1, which is, of course, 0. So we have, is 3 a factor of 0? Well, the answer is yes. Everything's a factor of 0. 3 times 0 is 0. So 3 is a factor of 0. We're good to go. It's true for the base case. Excellent. That's our gasoline for our machine. Let's do our inductive case. So that was 1. Our inductive case. Okay. Let's again assume for some k in our index set that 3 is indeed a factor of 2 to the 2k minus 1. So we don't really have a good algebra of divides worked out yet. So maybe it makes sense to write this in terms of algebra. So what does this mean? This means that I should be able to write 2 to the 2k minus 1 as 3 times some integer. Remember, that's what it means for a number a to divide a number b. You can write b as a times some other integer. So I call that other integer L. So for some L in the integers. Okay, so that's what we know. I'm going to leave a little bit of space here because I'm just going to do this kind of follow your nose like. And we'll see that maybe we're going to have to rearrange this in order to come up with something that looks a little bit more usable. So what do we want to show? We want to show that we can write 2 to the 2k plus 1 minus 1 as 3 times some integer, right? We want to show that this is true for the next number up from k plus 1. We want to show that 3 is a factor of 2 to the 2 times k plus 1 minus 1. Okay, so that's what we want to do. If you haven't tried this yet, this is an excellent opportunity to try and figure out how to use our inductive hypothesis. So start with 2 to the 2k plus 1 minus 1. See if you can come up with a way of using your inductive hypothesis. So pause the video and give that a go. Okay, now that we're back, we can see it'll be kind of easy to get this 2 to the 2k separated here, because this is just 2 to the 2k plus 2. We could just multiply that out. And so we could take out a 2k, or 2 to the 2k, and then use our inductive hypothesis there if we had that minus 1. But if you can try, and it was going to be really, really hard to be able to get that minus 1 with the 2 to the 2k. So let me kind of write down what I mean. This is the same thing as 2 to the 2k plus 2 minus 1, which is the same thing as 2 squared times 2 to the 2k. And you can see if we multiplied those, we would get 2 to the 2k plus 2 minus 1. And remember, this is 4. So really, what do we have here? We have 4 times 2 to the 2k minus 1. So we only have an idea of what happens when we have 1 2 to the 2k minus 1. But, and I said I'd leave some space, and I didn't, unfortunately. That's okay. I can just go up here and put it in. We can rearrange this. If we rearrange this for 2 to the 2k, that's a little bit easier to work with. So this is the same thing as saying we can input this line that 2 to the 2k equals 3l, adding 1 to both sides, plus 1. So now we have a nice way of using our inductive hypothesis. So let's go ahead and do that. That's just, by the way, just to make sure we understand what's going on here, I just rearranged this to be in a more usable form, because I know that if I just had it in terms of 2 to the 2k, I could easily replace that. So let's see what happens here. So let's go back up here. So this is the same thing as 2 squared, and now I'm going to use my inductive hypothesis. So this is going to be times 3l, 3l plus 1 minus 1, and that's by our inductive hypothesis. Remember, we assumed that 2 to the 2k equals 3 times l plus 1, so I'm using my inductive hypothesis there. And now let's simplify. So this is the same thing as, well, 4 times 3l is 12l. 4 times 1 is 4 minus 1. So this is 12l plus 3. And remember, we want to get this of the form 3 times some integer. So we'll factor out our 3 and we're left with 4L plus 1. So it looks like we did it. We started with 2 to the 2 times k plus 1 as our exponent minus 1. And we showed, using our inductive hypothesis, that we could write it as 3 times some integer. So what does that tell us? Since 4L plus 1 is indeed an integer, well, it tells us that 3 divides, or 3 is a factor of, 2 to the 2k plus 1 minus 1. And there's our induction there. Remember, the big idea here is finding a place to use your inductive hypothesis. Maybe it involves a little bit of rearranging. If so, just do it. It's not going to be a huge deal. There's other ways to go. Maybe you didn't want to rearrange. You could just add and subtract something here. So you'd get 4 times 2 to the k minus 4 if you did that. So maybe subtracting 3 and adding 3. Then you could factor that out and it would work. You'd get the same answer. But rearranging here might be a little bit easier to see because then you don't have to figure out what you need to add and subtract to make it work. Let's look at one more to make sure we know how this goes. This one's a little bit different, but the ideas should be the same. So we're dealing with sets now. Induction doesn't have to involve just numbers. It can involve sets or whatever. The idea of induction is totally fine to use however you want as long as it satisfies your conditions. Okay, so what do we have here? We have A is a set in some universe, and we want to show for n that is in the integers greater than or equal to 2, so 2 is our least element in this case, that if you take the union of all of these guys, you can think of it like an indexed union, if you like, from 1 to n, and then take the complement, that's the same thing as taking the complement individually and indeed taking the intersection of them instead. So it's a generalized De Morgan's law we can think of. This is a generalized De Morgan's law. De Morgan's law we talked about just for 2 sets, or we could think of it in terms of logical operations, 2 statements. But it does indeed apply for any number of statements, 2 or more. And this is how we're going to show it, is via induction. This holds for either 2 or more sets or 2 or more statements, depending if you're in the land of logic or the land of sets. Okay, so let's do our base case first. So proof, this is by induction. In fact, I'm not even going to do it. We already did it in a previous video. So our base case is when n equals 2, and this is just De Morgan's law. And I believe for sets, this is in topic 19. We proved that in topic 19. We don't need to prove it again. We're good to go. That's a nice thing about mathematics. Once you prove something once, unless you're asked to do it as an exercise or something like that, you don't need to prove it again. You can just use that. We know this is true because we've already proved it. Now we need to show this is true for larger values. So let's do our inductive case. Values larger than 2 sets. Okay, so let's assume for some integer greater than 2, we'll call it k, that if I take the union of all of those guys and then take the complement of that set, that equals the intersection of the individual complements. And we want to show that this is true rather than for k plus 1. But we can use this fact. So my suggestion here is trying this yourself. Remember, you want to show something equals. You don't have to start with the left-hand side. Maybe it's easier to start with the right-hand side. And looking at this, I feel like we might be able to use our inductive hypothesis a little bit easier if we start with the right-hand side and show it looks like the left-hand side. Since, and I'll tell you the reason that I think this, is that I have a bunch of constituents here. This complement of A intersect complement of A1 intersect complement of A2, etc. So they're kind of already separated for us. So I might be able to just separate off the k plus 1 set and use our inductive hypothesis on the other k. Whereas this way, they're all in one chunk here. It can be done, but it'll be a little bit harder to see. So pause the video now and try it yourself. Start with the right-hand side, show the left-hand side, and remember the other key is that we know that this holds, De Morgan's law holds, for 2 sets. We're going to use that fact again. Okay, now that we're back, let's consider A1 complement intersect A2 complement all the way to AK complement intersect A k plus 1 complement. Okay, and again, we're looking for a place to use our inductive hypothesis. So we're assuming that this holds. So if I bracket things like this here with those green brackets, well, now I can just say that this equals A1 union A2 all the way to union AK, complement of the whole thing. So this is where I can use my inductive hypothesis. So let's go ahead and do that. So this is the same thing as A1 union A2 union all the way to AK, and then the complement of that set. And I'll put some brackets around it just to be clear that that's just one set. And then I'm left with this intersect A k plus 1 complement. Now if we look at this, remember this here in our green bracket, we have a union of sets and then the complement. It's still a set. This is one set. That's kind of the key to this argument. This is just one set. So what we can do is we can apply De Morgan's laws for sets, again, with this set here in green bracket, with this A k plus 1 complement. So let's go ahead and do it. And just so it's clear, maybe if I called this set here just a big old capital A, what we have is A complement. So this is A is the union of all of the sets from A1 to AK. So it's A complement intersect A k plus 1 complement. So that's how we're thinking about that. And this A, this is just something that I defined right in the middle of the proof, just as a little explainer step. I'm thinking about this guy as a big old set. I'm taking the complement of this big old set that I called A. And if I write it to look like that, now you can kind of clearly see that by De Morgan's law, we can just get what we want. So let's write down what we're doing. By De Morgan's law, this equals well, it's going to be the complement of the other way around. A union AK plus 1. But we know A is indeed A1 union I wrote down a K, I want to write down an A2 union, all the way to AK union AK plus 1. And remember, these guys here are in brackets because we're thinking of this as one big set. But it's all unions between these guys. So we can use the associativity property just to drop those brackets. So maybe I'll just do that. So we'll get rid of this here. Let me clean that up a little bit, but that's the idea. There we go. And we're taking the complement of all of that. So we're good to go. We showed what we wanted. So we can write by induction the statement is true. And we're done. And again, the whole crux of this one was figuring out how to use your inductive hypothesis. So here, thinking about it, it would probably be easier to use your inductive hypothesis with the little kind of constituent parts with the complements rather than everything union together with a complement of that big union. So I started with the right side and I made it look like the left side using my inductive hypothesis. So here's where I used it. There's me using my inductive hypothesis. I'm assuming that the intersection of the complements equals the complement of the unions. So I did that. And then it's just a matter of convincing yourself that you just need to apply De Morgan's law, because we know that if we have a complement of a set intersect the complement of another set, that's the same thing as a complement of the union of those sets. So that's what's going on there. So hopefully that was understandable. And if you could do these, I think we did 6 induction problems in this section. If you're comfortable with these and you can do them, then that's great. In future videos, we're going to expand the idea of induction a little bit farther. And we're going to deal with cases where you might have to do a few base cases instead of one. It's like a generalized induction. And then we're going to talk about another type of induction called strong induction, where we don't just assume that it's true for k and we show it's true for k plus 1. We assume it's true for all values k and lower and show it's true for k plus 1. So they're the next 2 things we're going to talk about.